I know there's a few people here that recognize this. This is where I worked for many, many years, 24 years. I was one of the researchers and then chief engineer for the wind program there at NREL. Strangely enough, this is where my first job was when I first came to Colorado in 1977. This is at Rocky Flats, just underneath the Flatirons here, and this is where we get winds from 100 miles an hour regularly, and that is pretty rare for a wind site. Wind sites get high annual average winds, but not great peaks, and this is one of those sites that gets the high peaks, but not the high averages. So I love this place, and strangely enough, I'm still here. But I wanted to say just a little bit about evolution. I mean, this was the title of the talk, and I think many of you probably know all about this. But you know, in the mid-70s, there was quite a lot of wind energy research going on. But even way beyond that, or way before that, we had in the 1941 to 1945, we had a megawatt-scale two-bladed machine downwind. It was developed by Smith and Putnam. And that was done in, I think, in lower Vermont. You know, we talk about megawatt scale machines today as though, geez, we've really accomplished quite a lot. Well, maybe not so much. This is one of several megawatt scale machines that were of that era. And so I think that we are treading new grounds for sure, but I think we didn't invent some of this stuff. And there's some very innovative things about that machine, which I won't talk about, but it's a downwind machine. It has flexible blades. The blades themselves are stainless steel, but they're mounted on hinges. That was all to handle dynamic loads. A much more modern version of this is the Boeing Mod 5. This operated in Hawaii for many years, and this was in 1987. This machine was, and its predecessors were designed in the early 80s. And so this was, the first machine was 2 megawatts. This is 3.2 megawatts. And so machines that we're seeing regularly today, 3 megawatt onshore machines, we've designed these before. Of course, they look different. And that's the topic of another discussion later on. So I started my career before these guys, or before this one was designed, but way after this one. And thank goodness. Be well preserved. I think it's interesting. The economics are everything. Everyone knows that. I think that when we started really producing a lot of commercial machines back in the late 1970s, it probably was 1980. This was 1980. 50 kilowatt machines on aggregate in a wind farm were much cheaper than that two-bladed, teetered, downwind 2 megawatt machine that I just showed. We could put in more of these, more capacity with these, much cheaper than they could. And so I think NASA had to put on their thinking caps about, okay, how do we get to something that is economically viable? The Danes took a different approach. The Europeans felt like the way to get to megawatt scale machines was to evolve that. And I think through the 80s and 90s, that's kind of what was happening. I think we really abandoned the very large scale machines. There was some research going on, but really the commercial industry, fueled by regular support from the European governments, evolved their machines into lighter weight, lower cost, more efficient, more productive machines. And that really fueled this evolution, this scaling up. And as we began to develop a design process and document that in form of international standards and then develop supply chains, the industry grew. So there's a lot of stories that I could tell along the way, but one of the key stories is power converters. I think that all these early machines were constant speed, fixed pitch machines, very simple, but they sacrificed aerodynamic efficiency. And as we got larger, we realized the machines were dynamically active, and we really needed to be able to grow the machine without growing the dynamic loads. And power electronics allowed us to operate in variable speed. Variable speed allowed us to operate at constant tip speed to wind speed ratios, which allowed us to operate at the very peak aerodynamic efficiency. And that was one thing, but the other probably more important thing was that you could relieve all of these dynamic loads that come from turbulence in the wind. And we were breaking gearboxes right and left. We still break gearboxes right and left, but it was epidemic in the 90s. I mean, we have gearboxes that wouldn't last more than 3-4 years. And they were intended to last for 20 years. And so we really had to scratch our heads a lot about what's causing this? How do we make a gearbox that will last 20 years? And so on. Well, power electronics played a big, big role in helping us improve that, because they could control the torque very, very dynamically and very precisely. And so with that, and with the advent of cheap power electronics, which all came along in this era, we were able to put together larger converters, higher power converters, and now all machines are variable speed one way or another. So I think the interesting thing is, here we are, this is 2000, this is 2010, 2015. The debate was always about how big is the optimum. We knew we could make any size machine, but the question was, what's the optimum size for the best economics? And gosh, there were tremendous debates, rotor diameter trade-offs in every contract we had at NREL. And I think that it was always just over the horizon. It was always a little bit bigger than what we were building today. It's still that way. That debate hasn't gone away. But an interesting thing has cropped up. Transportation has been the new limit. And I'll talk a bit about that. So today, though, I think that we're on that threshold where we have to talk about offshore and onshore. The conversation back here was never about offshore. It was always onshore. Why would anybody go offshore? And now I think we have to talk about offshore in the same breath that we talk about onshore. Very interesting history. I mean, I love this slide because it's kind of my history. This is how I grew up in the industry and the things that I saw and participated in as I was growing up. So I'm still growing up. We have to talk about cost of energy. The whole story is about cost of energy. If we can't beat the established energy, then we're not going to succeed. Full stop. And I think that the short story is we're doing that now. I mean, through this decade of technology evolution and design process evolution and standards and lots of research, we've come down to a price that's competitive. And you're going to see some scatter in here. You always will. It's wind speed. It's site dependent. There's permitting differences all around the country. And so there'll always be a bit of scatter in there, but I think that the interesting thing is, if you've got a good wind site and you're not hampered too much by the permitting process, you can build some machines that and buy into a very inexpensive, the least expensive market. So this is the installed cost by lots of different sites, and $1,500 a megawatt. That's still the right price. Then actually it's getting cheaper. It's getting cheaper because the Chinese are making cheaper machines, and that's driving the competition. So I think that there's you're going to see this price come even lower. This is the total turnkey cost. That is the turbine cost, the tower, the foundations, the roads, the infrastructure. It's everything. And so turbines are costing somewhere down in here. It's less than $1,000. It's probably $700 a kilowatt. Pretty amazing in my mind. So what's the price? That is, what are people buying or selling energy for? Well, this is data from Berkeley Labs, and over time, this is from 96 up to 2015, and you see there's a hump in here, but you know, the big projects down here in Texas probably are selling for $20 a megawatt hour. And that includes, that is, they're selling into that market, and so they're getting the production tax credit along with it. So maybe that makes the actual cost somewhere in the 4 cents per kilowatt hour. You'll see in a minute that's actually less than that. So there's lots of evidence. There's different size. This is a great chart. I love this, but it shows that there's quite a lot of energy going in at pretty reasonable prices. This is the slide that I really like. Lazard puts this out every year. They look at all of the technologies and they look at the unsubsidized lowest or levelized cost of energy. And so I think that this is interesting because you've got one group that we think is pretty objective. They have no stake in any of the particular technologies as far as I can tell. So these are the alternative energies, and these are the conventional or established energies. So here's coal at lowest $65 megawatt hour up to $150 a megawatt hour. I think if Leslie was here, she'd probably say it's probably higher than that. Gas combined cycle 52, and nukes 97. I believe that's probably low, but I'm not sure. Gas, you've got gas peakers, they're pretty expensive. So we come up to some of the others. Efficiency, of course, energy efficiency is the best, you know. But wind, $32 a megawatt hour. And so if you add the PTC to that, then you can probably sell that energy for $15 a megawatt hour. And I've heard of projects being sold at $18 a megawatt hour in Texas. The production tax credit. So that's our government's way of subsidizing the or giving a tax credit to energy production. Yes.
What about
Ganesh?
offshore?
Yeah, different story. Offshore, I think that it's not in here. Offshore, it depends a lot on the wind resource and the bottom conditions and all the rest of it. The cheapest I've heard of is Denmark's Dong Energy put together a system that was recently that I think was $80 a megawatt hour. And that's the cheapest I've heard of so far. Generally, the $150 a megawatt hour to maybe, $130 a megawatt hour. And those are for bottom fixed, reasonably shallow sites. If you start talking about floating offshore, then it goes north of $250 a megawatt hour.
Do you have any idea about the first offshore number, Rhode Island?
Rhode Island?
Black Island?
I can't tell you what the cost of energy is there, but I'm sure it's pretty high because I think it's the beginning of a much bigger project. But Dong Energy is, I think, the contractor. And I think that that's paid for by Danish retirement funds, and they're Danish turbines, so it's a kind of a completely Danish machine project. But the hope is that as we go on, that same curve that I showed earlier will apply to floating offshore. In the US, we have a lot of deep water. I'm getting ahead of myself. I've got a slide on that. Let me go forward. So I love this slide, that slide, but here shows you where it is. This is 2014, and so you see a lot of stuff in Texas. Texas, I'm sure you can't read this in the back, it's 14,000 megawatts in Texas, and that was 2000. Excuse me?
Is there any offshore?
There is no offshore in Texas.
No, in the map.
Oh, no, there's no offshore in the United States. Full stop. Well, that's not true. What's that? Five in Block Island, but it's commissioned but not operating yet.
Actually, American Wind Energy Association, they just published the first offshore report, and they present upcoming 21 projects all over the United States, and 2 of them in Hawaii, and a couple of them around Oregon, and majority of the projects are in Northeast, and there is one, if it happens, it will be the first freshwater offshore, that's in Lake Erie, in Ohio.
Yeah, that's the DOE demonstration project. Yeah, there's a lot planned, and up until a few years ago, it didn't look like the planning. I mean, there was ambitions, but I think that there was low optimism that things would happen. Well, there is a process now. It's not an easy process, but there is a process that that is reliable and will allow people to do offshore installations. And the Bureau of Ocean Energy Management, BOEM, is the group that's in charge of that. It's underneath the Department of Interior. We'll see if they survive. But this project is pretty much on autopilot now. That is, so I think that it's something that would be very difficult to stop. And no, I don't think anybody really wants to stop it. It's good for jobs. It's good for energy. It's good for commerce. So I suspect that those will continue to go. But I've got a slide on that. So again, I'm getting ahead of myself. You're dragging me out. So yeah, this is all the onshore, and by far onshore is the cheapest, and always will be the cheapest. And so if you've got lots of real estate onshore and a good wind resource, that's the place to put wind energy. So there's the world annual wind energy, I think, as a percentage. Let's see, what is this? As a percentage of their consumption. Okay, so Denmark is the winner, and has been for quite a long time. They get almost 40% of their energy from wind on an annual basis, and their goal is to be way above 50%, and they're getting there. I think that they do that because they're in a unique location, sandwiched between Germany. What's that?
If you've ever been there, you'd know.
Yeah. 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 Are there any Danes in the room? Yeah. Okay, you know. Denmark's a wonderful place.
Ireland and Denmark is coming from the west.
Yeah. Well, so Denmark is right between Germany, Sweden, and Norway, and they have strong transmission between all of those countries, and from particularly Norway, which has a lot of hydro. They can turn it on and off whenever they need to. And so that the storage is sort of automatically built in. And so they can trade power back and forth with those countries at ease, and they do. And that's how they do this regularly. Denmark operates at well above 100% wind energy in the winter on a regular basis. Last year, Dong Energy, a friend of mine who's the technical lead there, told me that the average for them for the month of December and January was right around 80% of their energy came from wind energy. So high penetration, no question about it. And they seem to know how to do that. So Ireland, Portugal, Spain, and so on. You go way down here, and here's the US. And this was 2014, I believe. I think we're a little better than that now, maybe above 5%, 6%. China, they're below 5%, but they're gaining fast, and I'll show you a little bit more about that later. All right, so I can remember when there were conversations about, gee, how much wind energy could we really install in the United States? And in 2008, we got a group together within the Department of Energy and NREL and a bunch of other folks, and tried to write a report that said this is how we could get to 20% by 2030. And we very sheepishly put that report out there, thinking that it would be laughed at because it was so outrageous. Such a huge number, 20% of the nation's wind energy by 2020. How is that possible? Well, we've since, this is a curve out of that report, and we said, well, here's how we have to get there. If we're going to do it, we have to start ramping up, and we have to reach sort of a steady production level. And some of that is going to be offshore. This green slice that grows, that would be our projection on what offshore would be. Well, here we are in 2016. And the round dots are what we've actually done. So believe it or not, this is when the report was put out, and we've been staying ahead of our projected curve. Good news. Yay. But we have to keep this up and keep on going. And that's just to get to 20%. And 20% is probably not enough. But what did China do? China started late. We've been at this since the late 70s. China comes along and starts putting their first machines in 2006 and just takes off. And today, they've got, what is this? I think they've got almost 150 megawatts installed. Their goal is to be at 220 megawatts by 2020. They will blow through that, just like they blew through their earlier projections. They had projections, I think, for 2012 or 2014. They were somewhere down in here. They clearly went right through those. So I think China is on their, well, first of all, it's already the biggest market. It's on the way to continue to be the biggest market, and thank God, because they need it. We all need it. But they probably need it more than most. I was in Beijing a week ago, and I can tell you, it's for anybody who's been in Beijing, yeah, it's a beautiful city. And when it's clear after a windy day, wow, it's a great place. But when it's smoggy, it's a bit dicey. Nobody in China wants coal, I'm sure. They all want clean air just like we all want clean air, and so they're going after renewable energy like crazy. So anyway, the question was, is it possible? Oh, absolutely. If we have an attitude and a political will, then we can, there's no technology barriers to go to meeting 20% or much, much greater. So 10 years went by, we said, gee, we really need to revisit that report. A large group of industry members got together within the Department of Energy as a sort of an overseer, and the question was put, how do we get to 80%? 80% renewable energy. Let's don't talk just wind now, let's say all of the renewables, how would we get to 80% by 2050? And so this great report was put out. If you haven't seen it, you got to go to the website and download it. There's a tremendous amount of very, very detailed technical information as well as high-level information on sort of all aspects of what it would take to get to 80% by 2020. These are a few figures out of there, and they're kind of complicated and they require a little bit of studying to sort of fully appreciate it. But I think the interesting thing is they started with a baseline case and said, if we do nothing, where are we? We're about at, today, about 1,000 gigawatts of installed capacity in the United States. That's where we are today. And this is the mix. We've got coal, a lot of gas, we've got some wind, some solar, and so on. And if we were going to get to, this is the load growth that's sort of projected out to 2050. If we were going to get to 80% renewable energy, these changing colored lines are the things that would have to happen. We'd have to have more wind, more solar, and so on. So what does that look like on a percentage basis? If each year this is the 100%, well, we say, okay, here is the percentage of variable generation. That's this curve here. And it starts out with less than about 5%, maybe 8%, and gets up to almost 50% of the sources of energy being variable energy. For the utility guys, they don't like that. They're used to having their hand on the throttle, being able to turn the power plant on or off or throttle it to match their estimation of the load. They're always predicting what the load will be in the next 5 minutes, 1 hour, day ahead, and so on. So they don't have control over the load, but they do have control over their generation. Well, now we've thrown them a curveball and we said, you no longer know exactly what your generation is going to be. It's variable. And so that's the new challenge, and Tim can speak about that for a long time. But so that curve is significant. But I think the other interesting thing is we see wind energy, the slice that's accounted for wind energy, which is this tall pink one, gets larger and larger. That it has to in order to get to 80%. So here's the really interesting thing that came out of this study. If you look at what it's going to take, and here's the baseline scenario, there's quite a lot of feeling that load is not going to grow. We're going to get better at how we use energy. We're going to get more efficient, and so our load is not going to grow. It's going to level out at something here. And so if coal, if we don't turn off coal plants, if we have the same amount of coal, more or less, if the coal plants live out their natural life, then this is the amount of coal we'll have on for the next foreseeable future, till 2050. This is the amount of nukes, and what do we have here? Natural gas, CSP, wind, and so on. And so here's the point. Wind doesn't grow, PV doesn't grow, nothing grows if we don't turn off the coal. Here's the 80% scenario. The only way that we grow more renewable energy, the only way that we get to 80% renewable energy is to start shutting down the coal plants, letting them expire. Nukes stay the same. That part of it hasn't changed. Gas goes down a bit as time goes on. And wind energy, solar energy, and even hydro stays more or less the same. And so the challenge is to figure out how to turn off the coal plants. And that means huge economic changes. It's much more political than it is economic or anything else. So But I think that this all came out of that study, and I think it really is sort of the source of Clean Power Plant, the CPP plan that's coming out of the EPA. I think we need to figure out how to follow through on that. And let's hope it survives. Let's hope the EPA survives. Okay. Something else that has to grow, not just the number of energy sources, we need infrastructure. So if there is a bright light in our new politics, it might be infrastructure spending. Here's the distribution, or the transmission system that we have more or less today, 2010. And what we really need is something that looks more like this. These big fat red lines, those are transmission lines. We need better transmission to transport a lot of this energy from the high renewable energy centers like West Texas, where nobody lives, but there's an awful lot of wind energy, cheap wind energy. We have to be able to transmit it out of there in an efficient way. And so we've got to be able to transmit from the Midwest, which is where all of the wind energy is, or quite a lot of it, up into New England and to the East Coast. And most of the populations are along the coast. Most of the energy is in the interior. Wind energy, I'd say, and quite a lot of solar energy. So I think this is important. And people say, well, what would it cost? And this study said, well, somewhere between 2 and 5 cents per kilowatt hour. Is this thing? Yeah, 2 and 5 cents a kilowatt hour. It depends on a lot of things, but the low estimate was about 2 cents a kilowatt hour. Very affordable, in my opinion, to reach that kind of goal. So we commonly talk about, okay, with that kind of penetration, how do we maintain grid stability? And for those who work in variable energy and the grid, they understand that you've got to have some way to balance all of these varying loads. And so wind turbines were never required to behave like power plants. That is, provide grid stability in the form of frequency support, voltage support, and low voltage ride-through. Things that a normal power plant does and we never did, partly because we were never asked to. But when the utilities started to really wake up in West Texas and say, wait a second, we just had that whole 200 megawatt wind farm go down because of a high wind. They all went down on a high wind shutdown, and suddenly we've got a huge problem. We had to scramble and find out where the other energy source was going to come from. And so they said, okay, if you guys are going to be that dominant in these distribution grids and these smaller grids, we need you to behave like larger plants. And so they now have put a lot of requirements on the wind turbines. And it turns out that the wind turbines can actually handle that quite well, as well as the solar plants. Power electronics has given us the ability to make the wind turbines behave more or less just like power plants. And so now these turbines, because they have very fast acting power electronics, can actually do a better job of adding to grid stability than a normal power plant. And so those are realizations that have just come around. But I think the other piece is the variable energy. We have to introduce better dispatch agility. We buy and sell energy on an hourly basis. Wind turbines and solar can predict a day ahead very accurately, within 15%, how much energy they're going to generate in a particular hour. That has helped tremendously. So forecasting is playing a huge role here in making Denmark work, and other countries like Spain and Germany who operate at very high penetrations. And it'll play a big role in the US scene. And this is a graph that just shows actual measured wind, forecasted wind, and how well they've been able to track it. And there's two different approaches, day-ahead forecast and two-hour forecast. The two-hour forecast is this green line, and you can see it's tracking the black pretty darn well, plenty well enough for the dispatchers. They need to have something that's within 10%, because they always carry 10% of spinning reserve, and so that's plenty accurate for them to be able to manage their site. So given those two things, forecasting and power electronics that can add to the grid stability, they can do quite a lot. I'm going to zoom ahead. Cost of energy is the big issue here. and for technology, of course. And so what we care about is this turbine cost times plus the cost of capital plus operations and maintenance cost, which is really a measure of reliability, all divided by the annual energy. And so engineers concentrate on every one of those boxes. Reducing the capital cost, whether it means reducing the cost of the tower, or foundation, or the infrastructure, or the blades, they want to minimize that, but maximize energy. And there's a lot of different ways to do that and do it very reliably. And by the way, we want to borrow money as cheaply as we possibly can. This is my favorite video here. One of the things that led to reliable wind turbines is being able to design reliable blades. The blades, of course, are the core technology. We can't go to any other technology or any other industry and borrow that know-how. We had to do it ourselves. And one of the things that played a huge role in us being able to do that is to be able to test very large structures. Now, this is a fatigue test, and we built this building at NREL thinking that it would always be bigger than the largest blade. I think this is maybe the third blade we tested in there. So, and it's gotten even larger than that. So, and every country has these. Many companies have their own test facilities, and so it's just become part of doing business, and it's been part of the design process. You find these testing procedures and the standards now, and it's just integrated into the design process. So big credit to NREL for starting this. They weren't the first ones. The Danes were the first ones. They did it in a different way. And since then, I think a lot of people have followed this approach. Boston now has a facility. This is a cartoon of it. And for those who know anything about Boston, they drive over the Mystic River Bridge and you look down. This facility is huge. I think they can test something like 80 or 90 meter blades. So very important part of our technology. We now do similar things for dynamometers. We test drivetrains. And the NREL has 2 very large dynamometers to test drivetrains to make sure that they will last. So, but blades, I think that the story here is that blades keep getting larger and larger. I think that the key to getting to lower cost of energy is to design a machine, make sure that it works with a given rotor diameter, and then as you become more confident about its design limits, stretch the rotor diameter without stretching the support structure, the tower, the drivetrain, and so on. And so we've been very successful at doing this. This is just a picture of a typical production plant. All companies make their blades differently. And, some of it's very, very closely held secrets. But there is more fiberglass in that blade than there is in a 45-foot yacht. A lot more. And you've got 3 of them spinning out there. These are about 20,000 pounds each, and they're pretty long. And this is a truck trying to maneuver around a simple turn, and you see the articulation in the trailer. These are not normal trailers, and so our infrastructure can't handle transportation of these large blades anymore. They can't handle transportation of large towers anymore. And so this is one of the limitations on growing the machines. And so for onshore machines, we're sort of stuck around 3 megawatts. That's where blades have a chord length that's this chord of about 4 meters. And that's the magic number to get under bridges, even for trains. So that plus the tower bases happen to get to about that diameter at the same time. So we're sort of stuck right there. But offshore, we don't have any of those restrictions. They can make the biggest thing in the world and plant it offshore. And so manufacturing happens at quayside, and then they do some of the manufacturing offshore. However, so some very interesting innovations there. So the blades, materials have played a big role. We're still using e-glass. There's some carbon going into these blades, but mostly it's e-glass because you make the cost of energy trade-off, and you finally end up with that e-glass being a very lowest cost option. But there is some carbon. E-glass is it's actually called electrical glass, but it's the stuff that boats are made out of. and epoxy is the stuff that boats are made out of. But carbon is the stuff that airplanes are made out of. So, you know. So there's a lot of innovation going on in blades, thermosetting plastics, segmented blades. Transportation is one problem, so how about splitting the blade up into pieces and assembling it on site? People are looking into that. Joints are difficult in the field, and so when you've got a highly flexible, highly fatigued structure, joints are a real big challenge. So there's a lot of activity here, but someone mentioned controls. Controls have played a huge role in managing the dynamic loads. If you can pitch your blades fast enough to react to turbulence, then you can knock down a lot of the loads that drive some of these designs. So there's a lot of work going on in controls. Aeroelastic tailoring. Tailoring the aerodynamics of the blade to passively shed loads. There's two companies in Boulder, one Siemens, one is Envision, who are responsible for the rotor designs of their turbines. The Siemens office is right down on Pearl Street. Chief engineer there left and was hired by Envision, and now he works a few doors down at another company. So someone mentioned blades, that's who I would go to. Yes?
Shedding loads is unfamiliar to me.
So shedding loads, if your blades are constantly subjected to dynamic loads like a tree, if your blades can bend like a tree, then instead of being a rigid structure and having to support those dynamic loads, then it can flex and shed some of those loads. It's like a fishing rod. You can catch a pretty heavy fish with a very light rod because it's flexible.
So it's a desired feature.
It's a desired feature, but very precisely designed so that it behaves just the right way. If it twists in the wrong way, then you suddenly have worse loads. So it's a very tricky thing to design, but one of the things that is very unique to wind turbines these days is, okay, here's the tall tower story. Wind shear, there's more wind up higher. The higher you go, the greater the winds. And in some parts of the country, Eric tells me, that's even greater than we normally design to. So if you can make a very tall tower, then you can increase your wind characteristics and we increase your energy. Tall towers cost more money, and so there's always this cost trade-off. How high is just high enough? How high gets you the right cost trade-off? How high can we transport? You know, here's the optimum diameter, this red circle, and yet that's the tower that we could probably get through a bridge. And here we are with this articulated trailer again. I think it's taking special equipment to transport it. They're right at the limits. Well, what if we could build something like this on site? I think Eric in the front row that's what he's concentrating on, and others. Yes?
In 2008, I had some dealings with the Governor's Energy Office,
Mm-hmm.
and they were projecting that in Colorado, at a 50-meter hub height, we would have about 300 gigawatts available to us in wind.
Mm-hmm.
Then I know they raised, they did test at 80 meters, but do you know what the outcome was?
I don't, no. If you look at a map, and I'd invite you to go to Eric's website and look at the map for Keystone Energy, there's a map that shows you where the resource is at 50 meters and then where the resources are at 80 meters and 100 meters and so on. And you can see the area is steadily growing. And I assume that these are economically viable sites. So it's a pretty dramatic change.
The short answer is if you're in the plain states, you can get the pretty good wind at 80 meters. But if you're somewhere that has trees or rough terrain or anything like that, you got to get much higher to get to sort of good wind for good terrain.
Yeah.
Well, even in cities, I work in New York City, about 60 floors. If you looked at a sheet of plywood, it blew off the building.
Yeah. So Eric is, well, here's, what happened to my other, oh, geez. I had a picture of Eric's spiral winding towers that he can make on site. But on-site manufacturing, I think, is one of the solutions. Can you build towers on site economically and at high quality? And one concept here is to make concrete towers, build them on site. Here's a 3D printed tower, you might say, where concrete is the printing media. And it just sort of builds its way up. This is something that NREL is working with, but that actually is patented by a gentleman at Siemens. So, oh, here's Keystone. And there you can see, if you get close, you can see the spiral wind going up this this tower. That's lifted from Eric's website. I'm going to move along here. Gearboxes, drivetrains. I spent quite a lot of time on this. I like to say I've been breaking gearboxes my entire life. I started when I was in graduate school, and my first company, we broke gearboxes right and left, and then, well, I was working at NREL, we continued to break gearboxes, but then with purpose. We eventually started a collaborative to sort of look at why this was such a big challenge. Why was it, even with power electronics, so difficult to design a gearbox that would last for 20 years? And it turns out there's a lot of reasons. These gearboxes are very complicated internally, and there's quite a lot of flexibility. Gear teeth depend on very precise contact patterns to last. Lubrication plays a role, and so on and so forth. It gets very complicated in a hurry. But we learned quite a lot to help the industry do a better job. And I think today, I think we can say that we've got more than a 10-year gearbox. Most companies say that their gearbox is a 20-year gearbox, but all developers will say, yeah, but I'm going to plan one retrofit or one rebuild into that machine for the 20 years. So a lot, we learned a lot, but I think one of the things that I took away from this whole experience was direct drive generators make a lot of sense. Get rid of the gears and they can't fail on you. Well, direct drive generators are not simple either. This is a generator that was a design or prototype that my company, my last company, built, Boulder Wind Power. And it's permanent magnet machines with printed circuit boards as the stators, but it is large in diameter. This is not your normal wind turbine. And if you go over here and look at some of the others that are operating, here's Enercon, German machine, very large diameter generator, very heavy, heavier than a generator gearbox driven system. So the competition is, can I make this as lightweight as a gearbox and a generator for the drivetrain? And the answer is becoming yes, you can. This is a Siemens machine, a 3 megawatt machine, I believe, and or is that the 6 megawatt machine? They look the same. I think it's the 6. Huge machine. I mean, these nacelles weigh more than a locomotive on top of the tower, the nacelle and the rotor itself. And so you really are talking about a lot of weight, a lot of copper, a lot of magnets. Here's the Enercon's machines, generators being built. I personally believe that these are the machines, these are the drivetrains you'll see in offshore. Because in offshore, if you have to do maintenance, it is going to cost you 8 times as much to do your maintenance offshore as it does onshore. So you cannot afford to have things fail. And if they're going to fail, you want to know way before they fail so that you make sure that you can plant it into your system. So the drivetrain technology is changing the industry as well. But for the time being, gear-driven systems seem to be winning the game onshore. Yes, sorry.
Those rotors, are they sized that because of the torque?
Yeah, right. You have to generate 3 megawatts at 12 RPM here. There's 2.5 million Newton meters of torque here. And so...
And it's not possible to have several rotors, smaller rotors?
It is. Yep. You can have several rotors in series in smaller diameter, but the cost trade-off says you're going to be spending more magnets for that. So the diameter is your friend. If you can make a large diameter machine, you use less magnets and less copper. Now,
you're also interfering with the airflow.
not so much. Not so much. You'd be surprised. Actually, GE is testing a new concept where it's not a new concept, it's a really old concept, where they block some of the rotor at the center of the rotor up to 10%, and it actually improves the performance because it pushes that kinetic energy out to the better performing parts of the blade. So Siemens made that trade-off. You can trade diameter off for length, but it speaks exactly to your question. And they said, we want to be able to ship this machine, so we're going to go to more like I've forgotten what that is, a 2-to-1 aspect ratio. But you're exactly right. That's one of the trade-offs that we spent a lot of time on. Offshore, I think we've talked a little bit about offshore, and we've probably said this, but you know, the population centers are all along the coast, and And the wind resource, if you look along the coast, there's tremendous wind resources offshore. Not so much along the coast of Mexico or Texas, believe it or not, and the western shore of Florida. Too bad, because there's a lot of shallow water there. But as you go up into the northeast, a lot of great wind. You also get typhoons. So that's a new design challenge. But that's the rationale. And if you start looking at how deep is the water out here, that presents a whole new design challenge. So those are the two design challenges. And so here we are, say, okay, we kind of know how to build onshore machines. We can probably do better, and we are. But near shore, we've got these monopiles. Deeper water here, we start getting into these truss structures, which is very familiar to the offshore oil and gas industry. And finally, you start talking about floating. And this happens to be a tension leg platform. It's one of the technologies that's common in offshore oil and gas systems. But they don't have to build them as cheap as we do. So that's one of the differences there. So we're doing that. I think we have to go ahead and start. This is one example that's actually being tested now, and I think this was tested in Portugal, and now I think that this is one of the machines that's going in off of Coos Bay in Oregon. Someone mentioned Coos Bay or Oregon. There's one in China or Japan. Hitachi just put a 5 megawatt floating machine out in near Fukushima. What did someone say?
So this is floating?
That is floating, yes.
Can you explain the design, because it looks flimsy on that other slide. I can't really imagine how that could work.
This? How can this work? So if you have enough buoyancy, if you have a tremendous amount of buoyancy and these tendons are anchored, so you pull tension on these tendons so that there's so much upward tension that it exceeds any overturning loads. That's a typical, the offshore oil and gas industry does that all the time. And the beauty of it is that you have very little penetration through the surface, which is where all the wave action is, which is where all the wave loading comes from. So it's nice from that standpoint. If you have a big barge up here, well, that whole barge is in all the cross-sectional areas is subjected to wave loading. So a very different design challenge. So configuration trade-offs and for the lowest cost approach is common in this. I think we haven't seen the final configuration. And part of that trade-off is how easily can I float it out or float it back for maintenance? So it's not just the in situ cost, it's really the assembly, disassembly, maintenance cost. I'm going to push along here because you're going to start bugging me about time, aren't you? Okay, so there's our floater. There's another floater that's a monopile. And what you don't see is everything below the surface here. This is an 80-meter tower. What's below the surface, I think, is more like 120 meters. And it's ballasted down. So it's very deep and very heavy. That's a Siemens machine that's been operating out off of Norway for about, I think, 4 years now. So, okay. I have to show this slide because it's the best slide I've ever seen. For anybody who loves aerodynamics or flow visualization, this is fantastic. So this is an offshore site off the west coast of Denmark. It's Horns Rev 1. And the humidity is just right to create fog or precipitation behind the rotors. And so you can see they're all lined up. And if there's any question about rotors interacting, their wakes interacting, and where the energy is robbed from the downwind turbines, this makes it completely obvious. So we lay out rotors or lay out wind sites to minimize this interaction. But one of the things that's really exciting is NREL is working on computational fluid dynamics models that show that we can actually steer these wakes if we yaw the machines and point them up and down and avoid some of this and improve the performance of these downwind turbines. So we can look at a wind farm like this and actually say, what's the best performance I can get for the aggregate wind site? I might sacrifice some of the performance on this turbine to build up performance on these others by steering these wakes. Very interesting. But the design challenge for floating offshore is big. We've got currents and waves and typhoons and dynamics and bottom conditions and soil conditions all have to be simulated. They all go into the dynamic analysis of the system and go into a large optimization effort.
How much is ice an issue?
Ice is a big issue for the Great Lakes, for example. Norway has done a lot of work on ice flow and some fantastic, what do they call these? These are ice flow, they're like pools that you freeze a layer of ice and you have a tower in this pool, and then you force that ice sheet over the tower and measure the loads on the tower. So they have models for what the ice loading is, and then designs for ways to break up that ice as the flow goes over it. So yeah, big issue, and there's a lot of design recommendations and guidelines for icing, flow ice. Okay, last slide. I can't stop without saying something about birds. Because everybody that I talk to says, well, you kill birds. We can't have that. And I say, well, yes, wind turbines do occasionally kill birds, but relatively speaking, how much? And it's sort of, if you get pragmatic about it, and you look at what bird mortalities there are, I mean, here's 2.4 billion birds are killed by cats. 600 million birds are killed by buildings, windows, running into windows. And it goes on down the line. So way down here, half, what is it? There's 17,000 birds killed by wind turbines, and you think, that's a lot of birds. But then you look at, wow, that's not much. But I think that the big thing that I've gotten out of this kind of study, and Audubon Society has done some relative impact studies. Wind energy has a tiny impact, negative impact on bird mortality, but a huge positive impact on habitat. And in the next 30 years, we're going to lose 60% of the habitat for birds. You're going to see 60% of the bird species go away, and they know that. And they know that it's all about habitat. It's not about a few birds getting killed down here by something that's doing a much better job of saving the birds. So if it's displacing, if the source is displacing a carbon source, which is ruining the habitat, then you're miles ahead. So that's one thing. However, nobody wants to kill birds. And I think that we've done a pretty good job of looking at sites before we do installations and say, is this a flyway? Is this a site that's going to really cause problems? Well, let's not build there. Or if we do, let's figure out how to mitigate that. Let's figure out how to avoid killing birds here. And so there's quite a lot of creative mitigation going on. And I think one of the other things is, let's get quantitative about how many birds are really involved here. So this is a graph that shows the Horns Rev site. These are all towers, and they're tracking waterfowl. All of these little lines are waterfowl flying over this wind farm or across this wind farm, and these are all radar tracked. And you can see that they're all saying, wow, we see a wind farm coming up, we're going to avoid that. Some daredevils fly down the line, and some crossways.
Adventurous.
But I think the point is that birds are smarter than we think they are. They're not suicidal. And for the most part, they play well with wind farms. I won't say always. We've got a bat problem. We've got raptor problems sometimes. And so, it's not nothing. And I think that the people who are installing wind farms these days are very conscious about how to manage that risk and mitigate it. So I'll leave you with that and open it up to questions.